So let me introduce Jon. So Jon did his PhD in the University of Oxford and then spent some time in ETH and then worked as a research fellow. Now he's a professor at the University of Victoria in Canada, and he's going to talk about squaring the circle with simple.
All right. Yeah, thank you. Yeah, thanks for inviting me here and letting me speak in your colloquium. Very happy to be here. So we'll talk about some stuff related to something Tarski circle squaring problem. This is based on joint work with Andras Mate and Oleg Prokurko. So throughout this talk, we're going to be in k-dimensional Euclidean space. So Rk for k is a positive integer, but like really for pretty much everything we're going to do, you could really think about 2 dimensions or 3 dimensions. So for the purpose of visualization, let's just think of 2 or 3 dimensions. We've got 2 sets A and B, which are subsets of R to the k. And then sort of a key definition. Yeah, just let people get settled. Yeah. Yeah. I think we were 2 on time. Okay, just a simple definition. So I have a set A, a set B, an equity composition. Oh, thinking ahead, yeah, that's smart. So here's the idea. So you've got 2 sets. Let's think of them, I don't know, an R2 or R3 or something. An equity composition, what you do is you partition one of the sets, A, into finitely many pieces. You partition B into finitely many pieces. And you want to have the property that the AI, the ith piece, is congruent to the ith piece of B. So AI is congruent to BI for all I. Okay. What do I mean congruent? I just mean they have exactly the same shape and exactly the same size. So you can take AI and transform it with an isometry. Like think about translating, rotating. If you want, you can reflect and turn it into BI. So it's exactly the same shape. We say that the pieces, or the sets A1 up to AN, or similarly B1 up to BN, are the pieces of the equity composition. So like if you think of the pieces, you could think of like, doing like a jigsaw or something, putting together, pieces. And basically the idea is we have some pieces and we can put them together in 2 different ways to get 2 different sets. So you can put it together one way to get A, put it together another way to get B, right? If an equity composition exists, then we say that they're equity composable. So like a kind of little example, at some point I gave this talk in Brno in the Czech Republic, and my Airbnb had a chalkboard. And I needed an example, so I drew one. So like this, in some sense, the idea here is that this kind of irregular octagon is kind of equity composable to this kind of duck. And you can see, think of each color as being a piece. For example, the yellow here is the same shape as this yellow set here, right? One thing that this shows, well, demonstrates is that the pieces, it's not really like a jigsaw because the pieces might not be connected. So for example, like the green set contains a square and a triangle that are like a disjoint union, but it has the same shape, this is congruent to that, right? One thing I'm kind of cheating here is it's technically not an equity composition because I'm kind of not caring about the boundaries of the pieces. I'm not being careful, like between here, for each of these points, does it belong to the pink or the red? I'm not doing that, but essentially it's an equity composition, sort of, right? Any questions about this definition? Anything? Good. So probably like the most famous result on equity compositions is the Banach. I actually don't want to be, so for this definition, I'm going to say exactly, like, yeah, no, but in this picture, it's kind of modulo. So yeah, this is not really an equity composition, but it shows the idea, but yeah. but you want literally every single point to be correct. Yeah, which makes it harder. Famous result known as the Banach-Tarski paradox says that if I take a closed ball of volume 1 in R3, then it is equidecomposable to the disjoint union of two closed balls of volume 1, right? If you've never heard of this before, you probably think this is nonsense, right? Because it's, how could I take one ball and turn it into two balls? But that's why it's a paradox, right? I mean, essentially it seems to prove that 1 equals 2, right? Because you would say, you know, the volume of A is 1. If I partition it into pieces, the sum of the pieces, volumes of the pieces should equal 1. But if each piece of A is congruent to the piece of B, right? If B is two disjoint balls, basically they should have the same area and then or volume, and this kind of shows that 1 equals 2. But like, of course, this doesn't show 1 equals 2 because that's false. So that would be bad, right? I mean, math would be inconsistent. But yeah, so the reason this actually isn't you know, a contradiction. So the proof, I mean, basically the idea is that the pieces are going to be non-measurable, right? Which kind of means that they have an undefined volume. And therefore, when I'm doing this calculation, like the volume of AI doesn't exist, right? So yeah. Important thing about this proof, it uses the axiom of choice, and so it's non-constructive. So like it just shows it exists if you believe the axiom of choice, but it doesn't show how could I construct these pieces. It's purely an existence proof. Okay, so this is in 3 dimensions. Let's go down to 2 dimensions. So let's think about like what's the natural analog of the Banach-Tarski paradox in 2 dimensions. Well, the idea would be we want to turn a solid disk in R2 into a disjoint union of 2 solid disks, right? So, okay, so can we do that? I mean, when I first saw this, I was aware of the Banach-Tarski paradox, and I thought probably in 2 dimensions it's easier or something. But actually, it's just false. So in 2 dimensions, you cannot equidecompose 1 disk into 2 disks. In fact, so what Banach in 1923, he proved that, in fact, if you take a set in, or 2 sets in R2 that are measurable, so they have a well-defined area, if they're equidecomposable, then they have to have the same area. Okay, so you cannot turn 1 disk into 2 disks. You cannot take anything of a well-defined area and turn it into any other set of a larger area. Okay. Okay, so that kind of breaks any kind of Banach. There is no Banach-Tarski paradox in 2 dimensions, basically. So if I can't turn 1 disk into 2 disks, a natural question is like, what can I do, right? What kinds of sets are equidecomposable? In particular, what could I equidecompose a disk into, right? So a kind of challenge was raised by Tarski in 1925. So he asked, is a disk in R2 equidecomposable to a square of the same area? So can I take a disk, partition it into finitely many pieces, move those pieces around to get a partition of the square, right? Just kind of shift them and rotate them and whatever. Basically put together a jigsaw puzzle to get a square. Oh yeah, so such an equidecomposition, we'll call it a circle squaring or a squaring of the circle. I'll give you the answer to this in a few minutes, but let's first get a little bit of intuition and play around. And I'm going to show you that a certain strategy will not work, which is kind of the most natural strategy. Like when I first heard about this, I mean, what did I do? I sort of sat down and I like drew a circle. And then like, what if I cut it like this? And then now I've got my corners and now I'm going to rotate them around. I'm going to like try to cut things out and basically trying to do it using scissors, right? Let's prove that that will never work. So Was it clear what I? Oh, well, yeah, I'm not being too formal about what I mean by scissors, but imagine you had a big piece of paper, a big disk and a big square, and you want to cut the disk and the square into pieces so that if I take one piece, I can match them up so that this piece has the same shape as that piece, right? Yeah. Yeah, so an equity composition has they'll have finitely many pieces, and that's, I think somewhat important here. Yeah, infinitely many pieces would be a bit different. Yeah. Okay, so I won't be too formal by what I mean by scissors, but just think of what you would actually do with scissors. So I'm going to prove that it's impossible. So let's go by contradiction. So let's assume that somehow I did this using scissors. So I cut up my square and I cut up the disk into finitely many pieces, and I can match, the pieces up so that they have the same shape, right? So I want to show that this cannot happen. So what I want to do, take your partition of the square, and let's walk around every piece. So do a lap, just walk around. And at every point, if the piece at that point of the boundary has the same curvature as the disk that I'm trying to equidecompose into, and if it's convex at that point, so if it looks like, it's got the right curvature, and the piece is convex there, I'll color that point red. Okay, so for example, I've colored all of these points red because, let's say this has kind of the correct curvature, the same as the outside of this disk, right? Now again, walk around all of your pieces and do the same thing, but at points where it's concave and has the right curvature. Okay. So kind of roughly, it kind of looks like this. Oh, so yeah. Oh, yeah. In the second round, we're coloring a point blue if it has the right curvature and it looks like concave, like it kind of goes in. And now if you look at that picture, you can see everything kind of matches up, right? So if I look at the length of the red segments, it'll equal the length of the blue segments. But now let's do the same thing in the disk, right? On the interior, the length of the blue and the red matches, but the disk has all of these exterior points, right? The boundary of the disk, which are all going to be red. So here the length of the red is not equal to the length of the blue, but here it'll always be equal. So this cannot work. Any questions about that? So yeah, if you do not do this because you will never, it will work. Okay, so that's some argument of Dubin's Hirsch and Karush from 1963. And I mean, what they did was generalization of this idea, pushed this idea as far as they could, but essentially the idea is like this. Okay, so that just means you shouldn't use scissors, but it doesn't mean that there's no circle squaring. So kind of big result in 1990, Laczkovich. Oh yeah.
How could one state more clearly what is scissors?
I don't remember what the technical definition is, but somehow, yeah. You want like basically the boundaries to be like nice curves that have finite length, and because you could do curves that have infinite length, and because I mean here, to say that the lengths are different, they have to both not be. If I did some kind of curve of infinite length, then infinity equals infinity. So we need to have finite length curves. Yeah.
Still work because at the step where this curvature will be that way, like the
you're probably right. Yeah.
It's like I should be wrong, but only continuous curves on this. No?
There might be some technicality that you have to add, but I'm not sure. Yeah. Any other questions about this one? Yeah, there's some very specific thing that they did define something scissor congruent. But I mean, I don't remember what that definition was, but yeah. Okay, so Laczkovich proved, yeah, in fact, you can turn a disk into a square. Few kind of comments about his proof. So the number of pieces is pretty big. It's like 10 to the 50. Oh yeah, this is one kind of thing that is somewhat miraculous. That so we can basically in equity composition, you're allowed to use like any isometry. So you could like translate, rotate the pieces to make them look the same shape. But he can just do it just using translations. So basically you partition the disk, slide the pieces one at a time, do this 10 to the 50 times. And then it makes a partition of the square. Oh yeah.
Check with the first taking away from the
So these pieces, for example, don't even need to be connected. They don't need to be like, and the boundary, for example, could be two-dimensional. Like the boundary could be everything in the disk, for example, like the topological boundary. So it's a lot different. Yeah. These pieces don't have any sort of shape to them. They could be, for example, all a completely disconnected set. Yeah. Yeah, another thing about his proof is that he uses the axiom of choice, just like in the Tarski paradox. So this is perhaps not too surprising, but like it's kind of sad because if you use the axiom of choice, it's just an existence proof, right? It shows the pieces exist, and it doesn't. You can't go into that and say, like, what do they look like, right? So it's basically impossible to imagine his circle squaring. Yeah.
have to be non-measurable?
Nah, that's going to come. The answer to your questions will come up soon, but that is a good. In some sense, there's no reason because this disk and this square have the same area, so there's not really a good reason they have to have a non-measurable. They could be measurable, but his will not be. He cannot guarantee measurable by using the axiom of choice. Yeah. So actually, kind of related to that, given the fact that I don't know, this is not the Tarski paradox. We have the same area in the disk and the square. So this kind of raised a natural question. Could you have a constructive circle squaring? What do I mean by constructive? I'll say later, but for example, could you have a circle squaring that completely avoids the axiom of choice in your proof, right? Okay, so first step towards this. So this was basically various people asked similar questions, around the 1990s in different ways. And for a long time, nobody had any kind of idea. So a first sort of breakthrough in this direction was obtained by Grabowski, Mate, and Perkurko in 2017. So they proved, yeah. So to answer your question, you can have Lebesgue measurable pieces. Which, like I said, in the Tarski paradox, you cannot. There's no way to have Lebesgue measurable pieces because 1 is not equal to 2. But in this setting, you can. Unfortunately, their circle squaring is not fully constructive because actually they do use the axiom of choice, but it's kind of okay if you use the axiom of choice just to clean up a set of measure 0. Because that will not break measurability if you just change a set of measure 0 using the axiom of choice. So it's not fully it's kind of 100% constructive, meaning for measure 1 of the pieces in the disk, it's constructive, but there's a measure 0 for which it's non-constructive. Within a year, this was then improved to the kind of remarkable result of Marx and Unger, which says that you can actually take the pieces to be Borel, which, okay, I don't know how much measure theory people familiar with, but basically Borel sets are measurable, and they're even nicer than Lebesgue measurable sets. Yeah. It's possibly, it's at least 10 to the 50 pieces, or sorry, 10 to 50 pieces, but like maybe 10 to 100 or something. There's no improvements on that side, basically. And it possibly gets worse. Yeah.
Absolutely necessary to use Axiom of Choice, or you could use something pure version.
Oh, that's a good question. Or do you mean like so in the original proof or something?
Exactly.
That I don't know, because yeah, I don't exactly know what, if it's possible. Often it is the case that you can replace it with a weaker version, right? But I don't know the answer to that. That's a good question though. Yeah. But now it's shown that you can avoid it completely, so that's a much weaker version. Any other questions about that? Maybe I should say what I mean by fully constructive. So this is a constructive proof. So it's basically they construct their circle squaring using an algorithm. But okay, to discrete mathematician, I'm not sure if this will seem like an algorithm to you, but basically it's like you have like an infinite loop. Okay, you have some inputs like a disk, a square, and then some auxiliary sets that are like open and closed, like as your infinitely many of them as your inputs. You do an infinite loop, which to construct the circle squaring. So the output is a circle squaring. Within this infinite loop, you have infinite loops. Within those infinite loops, you have infinite loops, all kind of combining these nice inputs. And then the output of the final infinite loop, that the outside one, is your circle squaring. Okay, so it's constructive if you're allowed to do like infinite loops inside of infinite loops inside of infinite loops. That's actually not that bad. If you know what the Borel hierarchy is, that's actually only a few steps up the Borel hierarchy. So it's actually really, really quite nice pieces. Okay, so what did we do? If so this was a really big result. Basically, what we've done is improved on this in a few different ways. So this is a game with Andras Mate and Oleg Pokurko. So what we have obtained is a circle squaring, which, first of all, it's constructive in a simpler way. What do I mean by a simpler way? Well, basically, the whole thing can be described by doing one big infinite loop, where on every step of this infinite loop, you're doing like finite Boolean operations like union, complement, intersection, etc. So we take these kind of nice inputs like a disk and a square and some open and closed sets and just do finite Boolean operations and do one big infinite loop, and it outputs the circle squaring. So what this kind of, well, actually I'll talk about it in a second, but this corresponds to reducing the complexity in the Borel hierarchy by 2 steps or something. But the thing I actually like about the fact that you can construct this with a simpler algorithm is that it actually has some kind of benefits, because if you have a simpler algorithm for constructing your circle squaring, it kind of allows you more access into looking at how it's constructed and kind of analyzing the structure of the pieces. Because if you imagine things are happening inside of nested infinite loops, inside of infinite loops, inside of infinite loops, it's a bit hard to grasp the structure. Whereas we've just got one infinite loop, and as a result, we can obtain a circle squaring, which is, let's say, in a certain sense. All of this I'm going to make clear on the next slide. But so the technical statement is we prove that there exists a circle squaring. Again, we only use translations such that each piece is a Boolean combination of F sigma sets. Don't worry if you don't know what that is. It's just like, a little bit more complicated than open and closed sets. And the visualizable, so this is like the simpler construction is F sigma, Boolean combination of F sigma sets. And the boundary of every piece, so this is the visualizable part. The boundary of every piece has upper Minkowski dimension at most 1.987, which I'll tell you what that means in a second. But in that sense, it's kind of visualizable. Any questions about any of this? Yeah.
Is every group only using asset?
Yeah, actually. Somehow all the proofs basically, they take Laczkovich's idea and then just try to add things to it to like somehow taking translations was a really smart idea. It's kind of magic, yeah. Any other questions at this point? Okay. Okay, let's explain this like upper Minkowski dimension thing and how that corresponds to being visualizable. Okay, so imagine I've got like a better one. Okay. Okay, so let's say this is the unit square, right? And I've got a circle squaring. So there's some kind of underlying partition of this square into finitely many pieces that can be shifted around to make the disk. So you could think of it as every point having a different color. Let's say there's 10 to the 100 colors. Okay, we cannot distinguish 10 to the 100 colors with our eyes, but let's think you've got 10 to the 100 colors, and every point has one of those colors, right? So, okay, I want to be able to sort of visualize this. One way you could try to visualize it is on a TV, like on a television, right? So imagine you basically put like a n by n grid on top of this square, and underlying this, there's a circle squaring, but we're sort of gonna approximate the structure. Got an n by n grid. And like each of these squares, you should think of as a pixel, right? So it's a very high definition television. Yeah, as n goes to infinity. Now, I'm going to color the pixels, okay? And that's going to be my visualization of the circle squaring. And here's the rule for coloring the pixels. If I take one of these squares, if that square is completely contained within one part of the equidecomposition, so in other words, if all of the points in that square are really the same color already, I assign that color to that pixel. So if every single point in this square is blue, I give this blue. Of course, that's not going to be the case for all squares. So if, for example, this square has some blues, some reds, some greens, inside of it, then I cannot determine the color of that pixel. So I'll just color it gray. Okay. So of course, like if n is small, it's going to be all gray. I mean, and then maybe eventually you start getting some colors. And the way this is, I kind of can say that this is visualizable is that the number of gray squares is at most n to the 1.987 for large enough n. So if you do this representation, and you let n grow, you're only getting this many gray squares. So the area of the gray squares goes to 0, right? Because the total number of squares is n squared, right? So this 1.987 is what I mean when I talk about the upper Minkowski dimension being at most this. It's the number of gray squares when I try to draw it on a TV, right? Does that make, yeah. So that's the sense in which it's visualizable. Questions about that? Okay. All right, so yeah, let's, I guess, spend a bit of time talking about the proof. So the first idea, which goes back to Laczkovich, and really, this is, everyone's just copying the same idea since then, is to, it was such a smart idea, to think about everything inside of a torus So, and when I talk about a torus, what I mean is just like a unit square with the boundary missing, or sorry, half of the boundary is there, right? And let's scale down everything. So I've got my disk, and I've got my square, and they're both living inside of this torus, right? Okay. Now, when we're in this torus, we're going to do vector addition, but it's going to be modulo 1. So like things wrap around, right? Kind of like, I don't know if you played Pac-Man or something. Like when Pac-Man walks off the left side, he comes in the right side. We're going to do that. So if I add like this vector and that vector, you know, it'll shoot out, maybe make it longer. The side, like that corresponds, you know, that point or something, right? It's modulo 1. So yeah, 0.75, 0.6 plus, you know, that equals this, right? Okay, so I need to, so we're going to do things by translations. Here's what I'm going to do. I'm going to take two random vectors, uniformly at random. Let's say this one and this one. Okay, the reason I'm choosing them at random is so that they don't have any kind of weird algebraic like relations between them. You know, they're going to be quite independent, right? So just pick a random vector, pick a random vector. And basically translation vectors we're going to use in our equidecomposition are going to be integer multiples of x1 plus integer multiples of x2. So like 300 times x1 minus 500 x2, like very kind of simple integer combinations. And as long as we just use bounded integer combinations, it'll be finitely many pieces. Okay. To kind of try to represent this, we turn this into a graph. So yeah, I want you to imagine a graph where the vertex set is this torus. Okay, and then so basically in this graph, let's say I've got some vector v, where v is in the torus. Okay, so to describe a graph, I have to say what are the neighbors of v. So let's say that it's adjacent to like v plus x1. Okay, it's also adjacent to v minus x1. V plus x2, v minus x2, right? If this was all the edges, then if I continue this outward, I would just have a grid, right? Right, where this would be like v minus x1 plus 2x2, right? Okay, but across the diagonal edges, so I also want v to be adjacent to this and this. So all of these, so it's like a grid. But you have all of these like cross edges. Okay. So yeah, again, x1 and x2 are just random vectors, and from this I can construct a graph. It's kind of a weird graph, like from a graph theorist perspective. Like, I mean, each component here is definitely going to be countable, right? It's a countable grid, and then you've got uncountably many components. But yeah, it's a graph. Any questions about this construction? Okay. So let me kind of, oh yeah. Oh, that I'm using a what?
That you are adding additional randomness, but boundary for the Borel measurability.
No, I don't think so, because Yeah, no, I think that doesn't kind of hurt us. I mean, essentially, you could even choose these things in a non-random way. You just have to be more careful that you have some conditions you need them to satisfy, but it's actually weaker than just choosing, like, you don't have to choose them randomly. You just need some conditions, but a random pair will satisfy those conditions. But yeah, with probability 1. Okay, let me try to clarify the goal here. So now what I want to do, so I've built this graph. What I want to do is take each point in A, let's say A is my disk. Okay, for each point in A, I want to match, like kind of pair it up with a vertex of B at bounded, let's say 10 to the 100 or whatever distance in this graph. So that everyone in A has a unique partner in B at a bounded distance. Because if you've done that, then taking, let's say, a shortest path between those 2 points in the graph determines a translation vector, because it's like, if I walk from here to over here, that's like B, this is the vector like B plus, x2, x1, another x2, another, it's some integer combination of x1s and x2s. And if it's at a bounded distance, there's only boundedly many translation vectors. So basically, if I match everything, so the translation vectors determine the pieces in some sense. And let's not even worry about the 10 to the 100. I mean, yeah, we want some kind of bound. Any questions about that? You look confused. No? A is the disk, B is the, yeah, they're living in this torus. They could be what you want them to be. But yeah, let's make them disjoint. Just otherwise, I'm matching something to itself or something. And yeah, let's make them disjoint in the torus. It doesn't really matter though. So like if I look at any component, right? Some of the vertices in this component will be in A. They'll be in this disk. Some will be in B, and some will be neither, right? And I want to take everything in A and match it to something at bounded distance that's in B, and do this consistently, for all pairs simultaneously. It's got to be a bijection, yeah. I don't want two things to be associated to the same thing in B, because then it's not an equity decomposition. It's got to be perfect, yeah. Yeah, so we're gonna break this into a few steps. Although, yeah, so this is actually like a really amazing innovation from the Marx and Unger's paper. So they don't find this matching directly. They do this kind of intermediate step where they kind of find a fractional version of this of a matching. So the idea is, so try to find some kind of network flow, which you could think of as like, think of each of these edges as like a water pipe, and you have some kind of amount of water flowing through the pipe. And they find a flow in which every vertex of A has outgoing flow +1. So the kind of, it's a source of +1. Everything in B has -1 going out or +1 going in. And every other vertex that's not an A or B has outgoing flow 0. Which is kind of like, oh, and you want the amount of flow on every edge to be bounded, like uniformly bounded. It's kind of like a matching, because you could think of, if I match something in A to something in B at bounded distance, I could then take a shortest path between them and like put flow, like +1 flow going along those pipes to get to the thing in B. So so this is like a fractional kind of solution. You then need to round it to an integer valued flow. And the third step is to convert that into a matching. All of these details are quite technical. And so maybe I won't go into, when I say fractional, I mean that on any given, yeah, so at each vertex, it's an integer value coming in or out. but the actual flow on each edge could be, yeah, so it could be 1/2, 1/2, 0, 0, 0, or something like it. Yeah, it could be fractional in that sense. Maybe one thing I'll say about this first step is, I mean, basically, if you want to find a flow in a network, I mean, what does this come down to? For discrete mathematicians, you might think, I mean, it's like max flow min cut, right? And that's exactly what, I mean, okay, you need to do max flow min cut, but in sort of a constructive, careful way. But essentially, that's all that's going on here, that if there's no flow with bounded values on the edges, the only reason for that is that there's a small bottleneck, right? Because if there's no high flow, or there's no flow of it, you have to have a small cut, right? And actually, there's yeah, some amazing lemma of Laczkovich, which basically tells you that this is not going to happen. If I take you know, any subset of vertices in this graph, the amount of flow or the discrepancy between the number of points of A or B that are in that set is going to be small. But yeah, so maybe I'll yeah, let's not, I won't go into these kind of technical details and just say, yeah, oh yeah. Yeah, okay, maybe I'll say something about that, yeah. And you want to do it super carefully because you don't want to, for example, you could do it. Yeah, and the thing is, if you allow yourself to use the axiom of choice, you can just say, just do it. Yeah, compactness or something, and it's done. But of course, we can't do that. So we have to be extremely careful. Yes, let's talk maybe about the rounding. At a very high level, so here's how the kind of rounding works. I'm gonna take a subset of the torus, which when I look at the graph, this sort of structure, it breaks up into sort of blobs. Look at these kind of orange blobs, which cover like a high percentage of the vertices, let's say. Maybe this, I don't know. Okay, maybe high percentage here is like 40%. I don't know how much this is covering, but so you do some kind of partial covering of the vertices with these nice kind of nicely spread out, not too complicated blobs, which you can find in a kind of nice way. Now for each blob, here's how I'm going to round it. So look at the boundary of that blob, and let's think about the triangles. So this is actually why the cross edges are quite useful. You know, on this boundary, you're going to have some triangles where, say, 2 vertices are inside and 1 vertex is outside, or 1 vertex, like basically triangles that go across the boundary. So these 3 edges might be carrying a fractional flow. What I could do is just shift them all slightly to make this purple edge integer. Just shift it to the nearest integer by just circulating some flow here. But now, of course, the other ones are wrong. So I go to the next edge and I shift this one to be an integer. Of course, now the other ones, you know, we have to sort of, so we do this in a sort of 1-by-1 way. And there's some kind of magical nice thing that if I make an auxiliary graph on these triangles that intersect the boundary, they form an Eulerian graph. So if I say 2 triangles are adjacent, if they share an edge, that forms an Eulerian graph. You can just walk around this Eulerian tour of triangles, fix one of the edges, and eventually all of the edges leaving this set are correct. Just actually. Yeah. So what this is doing is just making the boundary of the blob integer. But then once all of this is integer, we use something called the integral flow theorem. So this is just a finite set. You can just replace that with an integer flow as well. Okay, so I've kind of, on every one of these orange blobs, I've made this integer. And that can all be done in a nice kind of constructive way. But which the idea then is to zoom out and blobs and put blobs around them to cover more of the vertices. And basically, we're going to round along these boundaries, and fix the flows inside so that they match up with what we did before on the orange blobs. Anyway, it's all kind of technical, but basically, this is our infinite loop is the levels of this covering. We're kind of covering the graph slowly and slowly and slowly so that everything gets covered, and eventually it gives you this flow. Yeah. Yeah. Oh, 10 whole minutes. Okay. I mean, I don't think I really need 10 minutes yet. But are there any questions about this part again? Okay. Okay.
Be fractional or could be real value?
It can be real value, although in our proof, okay, there's some technicalities. Actually, we don't. Okay, yeah, it can basically it can be real valued. So in Marx and Unger's proof, they construct this fractional flow also in a step-by-step manner and take a limit. And then when you take a limit, if you have rational values before, they may be non-rational, right? Actually, in our proof, though, we're always using an approximate flow. We don't take a limit, so actually they are rational, but we're only using an approximate flow, which gets better and better and better. It's all a little bit technical, but yeah. So just to with this, now I have these blue blobs, and everything would, and I would zoom out again, right, and just some blobs and keep zooming out, and that's where the limit comes from. Any other questions about that? No, it's not going to be fine. I mean, because even this graph goes off to infinity in every direction. But basically, we want these blobs to have kind of a good enough, have some control about the separation between them, and also the measure of the sets that they cover. So we want them to cover let's say a growing measure of points. We also want their boundaries to not be too ugly, because we're going to need to put these things around them later, and it's just going to be complicated. So yeah, I think you want nice kind of boundaries, and you somehow want in the end to cover everything. And okay, and it is even more complicated than that, but I don't want to get into those details. Yeah. Okay, so the last step then, so let's suppose you've got an integer valued flow. So yeah, again, every edge has an integer amount of flow on it. The flow out of any vertex in A is 1, out of any vertex of B is -1, and 0 otherwise. Okay, so we need to turn this into an equidecomposition. Yeah, this is okay. The idea of that is we take some kind of set of points, like these white points. To have is that are twice kind of far apart, and it's maximal with that property. Perhaps let's worry about. You break your grid into a Voronov. I mean, I'm taking, this point is this white is. So the cells are defined by, and then you can see that basically in any cell, the number of points in A and the points in B. And you can kind of to match up any excess with neighboring voice. Perhaps not going into more detail about that, but and so yeah, so that's all I wanted to say. And thanks again for the invitation.
Are there any questions?
Yeah.
What if it's not a square? What if you want to turn a circle into something else?
Yeah, I probably should have even said that. So all of this is much more general than circles and squares. And in fact, it's also higher. Okay, maybe I'll just repeat it. So the question was like, what if you're not dealing with circles and squares? What if you're dealing with different sets? Actually, yeah. The kind of most general theorem says, you know, you've got in, let's say, R to the K, bounded sets with the same measure. So they have the same volume. If the upper Minkowski dimension, which is this thing about this, remember this TV screen thing with the pixels? So if the upper Minkowski dimension of the boundaries of A and the boundaries of B are both less than K, and equity composition from A to B. Okay, this is in fact what Laczkovich, using and only using translations. So this statement actually goes all the way back. If these things are Borel, then the Borel structure and also the yeah.
So where does it come in the proof that they have the same area?
Well, in your graph, a typical subset, let's say you take a set of vertices in your graph. Well, kind of on average, you're going to see more twice as many elements of D as you see of A in that subset. Let's say you take within this grid, take some rectangle. Yeah, usually it's just twice as many points of A as whatever. But that means if I wanted to find a flow from A to B, basically a lot of flow. Basically, the capacity on any edge is going to calculate. So, like, basically, one thing typically.
Yeah.
Being point like the number of loops. How do you treat it formally?
let's say the first step of the algorithm, maybe there's some, or maybe the first 1,000 steps, there's some subset of the div where for example, this it is now after we say 1,000 steps. At this point, it has been determined which point it matches to in the other position. Okay, and basically, we do more steps. There's more points that get determined where they match to the other competition. And sort of, if you think about running this to infinity, eventually not just a measure one, but every single point, eventually there's some set. So for this point, maybe on the one trillion step, it's and for this one, it's the one, it's 1,000 steps, the image is you can kind of think of it as
But when you say points, you mean steps, right? But there are non-countable number of points.
each step maybe like uncountable number of steps.
Okay, yeah.
So each step you're getting. Oh yeah, I don't mean exactly one point. I mean, but I mean for every point there's one.
Yeah. Okay. Thank you.
Do you need to talk about algorithm, or is it everything like formally just captured in this like max flow min cut? What, or in some sense, what you need to? Yeah. You want to kind of ensure existence of a flow, and that you just use min cut for this, right? Or is it, or no, not really quite. It's yeah. I see. Okay.
Make it constructed in a way that not doing things like taking a lot of limits or something. Because if I take limits, that's like nested infinite loops and stuff. So I need to do it very, very carefully. When it max flow min cut explains why.
Finally, is the image at the beginning of your talk what you simulated in this story, or is it just a lie?
Basically, it's like you can't see the part of that. No idea. But there's so much.
Again, John, what did you